Okay. Live. How are we doing? Doing good? Ready to go?
It's in here.
So hopefully you have understood 34. No?
Can you do like D through D? Because yeah.
Okay, so recap on 34 is so projectile is shot up from ground level. Initial velocity is 30. So let's just quickly recap everything, I guess. Your velocity function would be initial velocity plus acceleration times time. And this is called g. This is acceleration due to gravity. And then the position function, the height, would be the initial height of 0 plus 1/2 at squared. Everyone okay with that? Okay. And then sorry. Got this mixed up there. 1/2 at squared plus v naught t, right? That's what we've all got. And then the h naught is 0. Which of course you can simplify to this. This is what we did on Friday, right? Okay. So this number comes up a lot because 4.9 is half of 9.8. Cool beans? Okay, so there's the velocity function. There's the position function. And so if you want to know something like how long will it take to reach its max height? Okay. This is where you start thinking more physicsy than just in a pure math sense. Because you go, well, if I was at my max height, then my velocity would be 0, right? So if my velocity is 0, I can set this equal to 0 and solve. So let's do that. So if you solve that, you end up getting 30 divided by 9.8. Okay, which is roughly 3.06. Thanks. By the way, this should hopefully make intuitive sense to you, because if you understand what acceleration is, if this calculation doesn't make intuitive sense, you might not quite yet understand what acceleration means. So you might want to try to think about that more, or we can discuss it together or something. But this is how fast I was going. What is acceleration? It's how much velocity you're gaining or losing per second. So this is how much velocity I started with, and I lose 9.8 meters per second each second, then I could simply divide the numbers to get the time it takes to lose all that speed. So I think it's pretty important to understand that idea, and not just, if you find yourself just being like, well, I don't really understand the numbers, but I'm plugging into the formula, things are going to be getting much harder and harder as the class goes on. So anyway, try your best to make intuitive sense of that. So anyway, then what? How high would I be? Yeah, plug it into, well, you have two options actually. Let's compare them. Clearly, I should be able to plug in the t-value into the height function, because that's what the height function tells you, is how high is the ball, right? So let's try that. So h max, so just to clarify here, D, the answer to D was 3.06 seconds, and the answer to E is this. So this is nothing wrong with this method, but this is sort of the vanilla. Does anyone think they know a sneakier way to get the answer very quickly from this number? I'll give you a hint. Think about average velocity.
Sloping every time.
No graph necessary. So think about my velocities. I started off at 30, and I ended up at 0. And that was during a period of constant acceleration, right? The acceleration was negative 9.8 the whole time. So what was my average velocity then? 15, halfway between 30 and 0. So it stands to reason that if I travel with an average velocity of 15 for that much time, how far would I have traveled? 15 times that. Roughly, what, 45-ish? Maybe 46? 45 and some change, exactly. So let's see if that answer agrees with plugging into the formula. Well, before we move on, does that make sense, that argument? Okay, it's an average velocity argument. Okay, so then calculator obviously would be helpful here. This is like 90 something minus whatever that is. And I don't know, I'm just trying to do this in my head. I bet it's 45 something. I don't know. Did someone punch this into a calculator? Anyone? No? Okay. Just rely on me. Don't worry, guys. I got it. So this is going to be approximately equal to I'm not sure if it goes up to 46. 45 point something, I'm betting. Maybe 46. Kate, are you gonna? Thanks, Kate. You're the best. You're national treasure. Book of secrets. What'd you get?
45.91.
Oh, almost 46. Okay, so this thing went almost 46 meters into the air. Yay! Okay. By the way, just throwing this out there, if there was air, we always neglect air resistance. Well, most of the time we neglect air resistance, unless otherwise stated in a class like this. If there were air resistance, would this be bigger or smaller? Smaller, for fairly obvious reasons, right? The air would tend to slow it down quicker than without the air. Okay, so then the next question, that was part E. Part F, when does the projectile hit the ground? So there's a symmetry answer to this, a nice, simple answer, which is there any reason why it should take more time to fall than it took to go up? I mean, maybe there is, I don't know. But if you think about the math of it, you're going from 30 to 0 at a constant acceleration. So wouldn't it take the same amount of time to go from 0 to 30 at the same acceleration? Like, it's symmetrical. So we know the total time has got to be double this, so 6.12. If you want, if you don't find that convincing, if you're like, well, okay, I get what you're saying, but that's not exactly rigorous, is it? What you would do is simply set h to 0. Let me show you that calculation, because it's actually pretty interesting how you get the exact same answer. So if I set this equal to 0, so if I say let h be 0, we get, so set that equal to 0, and then factor out the t. Oh, it's getting real shadowy in here.
This little sun came out.
Mr. Sun.
Yes.
Sorry. Don't want to close it. I have to. It's sad. Oh, man.
Pricing.
Yeah, we get like no sun, but it has.
Huh?
Get No sun, no winter time.
No.
Go outside.
What about side?
You're in sitting there soggy ground.
Yes.
All place.
Have you been I believe?
Sorry. Well, I was recording this and it's like the board is, it's, you know, like super bright white and then dark. It's like probably impossible to see. But now it looks okay, I think. Okay, so if you solve this, right, you get either t equals 0 or this expression has to be 0 because their product is 0. And then look, if you solve this, you get 30 divided by 4.9. Again, I'll use my superior calculation techniques. I'm going to say 1, 2. But you can see there that this is one of the things I think makes physics very interesting, and math in general, is you can think about something in different ways and show how those different ways of thinking about it were actually equivalent at their root. They're the same. So setting the height function to 0 for hitting the ground is the same as using a symmetry argument for the amount of time it takes to come down. And then lastly, how fast is the projectile traveling just before it hits the ground? Huh?
About
30. Again, this is neglecting air resistance. So say you weren't convinced. You're like, oh, are you sure it's 30? I don't know. Well, could I just plug my time value into my velocity function? Yeah. If you do that, you'll get negative 30. With rounding errors, it might show up, you might get an answer a little bit different, but it should be negative 30 in theory. Again, nature is highly symmetrical. The time it takes to go up is the same as the time it takes to come down. The speed that it came up with is the same as the speed it came down with, etc. So anyway, for soccer players like you, Kate, it's good that there's air resistance, because that if there was no air resistance, then if the goalkeeper punted the ball, it would by the time it came down to the surface, it'd be traveling the exact same speed that it left the goalkeeper's foot with. So then, like, heading the ball out of the air would be equivalent to just getting it punted straight into your face. So the air luckily slows the ball down during its path, and so by the time it gets to you, it's not going quite as fast, which is nice. The thing about air resistance, which is nice, is like air resistance always slows stuff down. So like when they punt the ball like this, the whole time, like, oh, okay, when he's right here, he's traveling this way, well, air resistance pushes him the other way. Say when he's over here, he's traveling this way, the air resistance pushes him the other way. So the air resistance is always opposing the motion. So it always tends to slow the ball down. At no point would it be speeding the ball up.
I feel like the balls are really, really high. And those feel a lot better than the laser beams.
True. It's also, if someone hits the ball into your face from 5 yards away, it hurts a lot more than if they hit it way up in there, because if it takes that long path, it's had all that time to be slowed down by the air. Okay. It's interesting though, if you throw air resistance into these models, it becomes very complicated very quickly. Because this is complicated enough. I think hopefully you'd agree. It's not easy. But it's all algebra. Once you throw in some air resistance, now you need some pretty powerful calculus tools to be able to analyze anything. So anyway, if you're wondering, why don't we throw air resistance in? We kind of do, but it'll always be qualitative. It'll always be like just some general, like I was asking you a second ago, it'll be like, oh, well, here's our answers, but if there were air resistance, would this number be bigger or smaller? Would this number be bigger or smaller? All righty. Let's move on. Thanks for asking, Julie.
Thank you so much.
Answered? So, at this point, I don't know, I think you guys have everything you need to know. Maybe let's go over one more example. I don't know, 39 sounds interesting, I guess. So a rock is dropped from a building. Just before it hits the ground, its speed is measured to be 49 meters per second. There's two parts to the question. One's a little bit easier than the other, although they kind of go hand in hand. Take a minute, see if you can set these up. And I'll give you a big hint. Pretty much every question we're going to cover for the next while is going to be governed by those two equations. So every question, you can pretty much start off with like this is how you model velocity when there's acceleration. And this is how you model position when there's acceleration. And the rest is more of the, so that's the math of it. The physics of it is kind of like making inferences like, well, if you drop a ball, what does that mean to drop, or a rock? What does it mean to drop a rock? Things like that. Can you correspond the time value? So anyway, so take a minute, see if you can get it set up. Try your best. I just realized it says tower. Sorry, I didn't. It's not supposed to be confusing. It's like a typo. Just it's a building, it's a tower, whatever it is. Did we get something set up?
Yes.
Okay, so that first part is actually a very simple question. It's just how long would it take if something's gaining, how much speed does the rock gain each second? 9.8 meters per second, right? That's when something's falling, it's gaining 9.8 meters per second of speed every second. So really just asking, if you're getting that much speed each second, how long would it take you to reach 49? So effectively, you're just going to be dividing 49 by 9.8. If you want to do it in a more equation-y way, it's V naught is 0. So when you drop something off a building, okay, when you drop something, drop means that the initial velocity is 0. And so my equation is V equals 0 minus 9.8t. Okay. And then this is 49. Now, if you're wondering about the negative sign, well, technically, if I'm going, when it hits, just before it hits the ground, its velocity is negative. So I really ought to call that negative 49. So anyway, you can see that's why I'm dividing 49 by 9.8. So that turns out to be like what, 5-ish? Huh? 5 exactly? Oh, wow. Neato burrito. Now the question is, how tall is the tower? Once again, we can get sneaky. We can say, if the velocity went from 0 to 49, then his average speed was 24 and a half. Right? Halfway between. So 24 and a half times 5 should give you the distance traveled. And the distance traveled is the height of the building, right? Or, again, let's say, okay, I don't like that. I want to use the equations. It's fine. Just take your equation, say x naught would be the height of the building. So this is the height of the building. Call that h. Plus 0. I can say 0 times 5 if I really want, I guess. But initial velocity is 0. And then plus 1/2 times negative 9.8 times 5 squared, because the time is 5, right? And set that equal to 0. Because when I hit the ground, my height is 0. Make sense? Initial height is how tall the building is. Final height is 0. If you had to do all that, that's just nothing. And so there's your 4.9 times 25. And what does that come out to be? 245. Wait, isn't there a decimal there? Hey, come on. Do you need someone?
Oh, I'm just watching you smart people at work here.
Oh.
Actually, I have a quick question for Winslow, Julia, Taylor, and Aaron. Are any of you attending the college fair today at 1 o'clock? It's in the theater. It's super cool. Quick oversight, then you can go home and you can get registered for a $1,000 scholarship. Okay, but tell me your names if you're going.
Taylor.
Taylor? Julia?
Winslow.
Yep. Aaron, no?
No, I don't think so.
Okay. I'll call you out of class around 1:45. Who is that?
Hatfield.
Oh, I got you down. I just didn't get to the AP Gov class to get the names, so.
Okay. So, but before, are there any questions on that, guys, before we move on? So, anyway, just to recap real quick, the point of this here is you can just stick to the equations, right? So especially if you're having a hard time understanding stuff. Or you're stuck on a problem. You can always come back to there's these two equations that govern everything pretty much. So I can just plug into them, solve. I definitely would encourage you to try to, push yourself to think of it in more intuitive terms if you can, because you'll understand it a lot better. But yeah, so let's move on to this is 41 is a classic physics question. We've done a couple of ones like this where we derive an equation. Huh? What? I'm not creative, Aaron. I could make it you're dropping they're dropping a watermelon off of a Ferris wheel. It's all the same. You can apply this stuff to any projectile, anything falling or going through space from any height. Yes, I'm sorry they're not very entertaining.
Albert and Bob.
Albert and Bob.
Maybe.
I just don't think you're gonna sit and draw a wrong around the building.
True.
Just get all
Small.
If you have a controlled environment, it's fine. Safety, no one's around, you can do it.
It's like spitting out the safety.
I can go with that.
So, on a question like this, you want to make sure you read it really carefully. And we need to go over what some of these, just the way it's phrased, like what the phrasing means. So, a rock is dropped off a building of height h. So, you got to be very specific. When a problem's given to you like this, the letters they give you, you got to use them that way. So, when they say, a rock is dropped from a building of height h, you can't go, I'm going to call that y. Unfortunately, you can't do that. If you're just solving a problem and it says, oh, find how much time this takes, then you have a bit more freedom to like choose your variables. But on problems like this, you got to make sure you're using the variables as given. So anyway, here's the rock. It's dropped from a building of height h. And we're writing an equation for the time it takes. Oh, by the way, this is 41. Sorry, Griffin. So it's number 41. So write an equation for the time it takes to hit the ground in terms of h and g. So when it says, who thinks they know what that means?
Of height and.
Gravity.
G is the 9.8 that we're familiar with, right? But what I mean is, when it says in terms of h and g, that means that those have to be the only variables in your equation. So it has to look like, well, sorry, I shouldn't say. That's only variables on one side of the equation. The other side of the equation is going to be what letter? T. So let's take our famous formula. And say you're just looking at it on a formula sheet. And it says, oh, x equals x naught plus v naught t plus 1/2 at squared. Now we're going to take this formula and use it for this problem. So what is x naught in this question? What is the initial position? H. Height of the tower, h. What's v naught? 0. Okay, so this term just goes away. And then here, what's the a value? G. Now here's where it gets a little interesting. I mean, should this be a minus sign or a plus sign? Think about that. By the way, what's the final position? 0. So my final position is here. This will radius to the ground too. So this is the equation. Now do you see, should this be a plus sign or a minus sign? Who can think ahead?
Minus, right?
Should be a minus. Why should it be a minus? Yeah, it's kind of interesting. I mean, if we said that, it actually depends on how you want to define what does G mean. If G is 9.8, then this needs to be a minus. If G is defined as negative 9.8, then this is a plus. But if you're looking ahead, what's the last step we're going to end up doing algebraically in this question? Square rooting, and just aesthetically and stuff. I'm not going to want to have any negatives under my square root. I don't want to have a formula where there's a negative variable, and I go, oh, yeah, but that letter represents a negative number. That's going to be confusing. So anyway, let's solve it. Move this guy over here, I guess. This is your first step. Oops, sorry. What am I doing? Don't look at that. My mind is TikTok and Walmart. Okay. How do I solve? What do I do? You don't have, just someone throw something out. What can I do here? I'm trying to get at that t. Too early.
Multiply by 2.
Multiply both sides by 2. Very good. So multiply both sides by 2. And you've got g times t squared equals 2h. Now what? Divide both sides by g. And we square both sides. So, there we go. That's that's a formula now where, do you have to memorize this formula? No, definitely not. This formula just comes straight from this one. Okay? Now what this tells you is that you now know a direct relationship between the height of a building and how long it would take for a rock to fall from the building to hit the ground. Moreover, let's say you did an experiment where you had a whole bunch of towers, right? So here you had a little small tower, and like a bigger tower, and an even bigger tower, and so on. Somehow you had an array of increasingly large towers. So you graphed the height of the tower on this axis, and then you graphed for each tower, how long does it take for a ball to fall off the tower? What would this curve look like? Where's the H? Look at the H. Where does he live? He's under the square root. So this is going to have behavior like y equals root x. It would look like that. Does that make sense? Sort of? So for example, doubling the height of the tower, if you made the tower twice as tall, does that double the time it takes for a ball to fall? No, what does it multiply the time by? If you double the height of the tower. The square root of 2, who's that? Very good, Colin. Square root, multiplied by root 2, 1.41 roughly. We'll get into that in more detail later. Okay, next. Write an equation for the rock's velocity just before it hits the ground in terms of h and g. How do we do that? What? Very good. So start with this equation. My velocity should be v naught plus acceleration times time. So let's see, what have we figured out? What's my v naught in this problem?
Well, I'm saying, so it falls, so it would be negative 9.8. That's weird.
Well, I'm sorry, maybe you're answering a question ahead of me, but v naught is 0, right? So are you saying that you were already looking at this term? You'd already counted this one out. You're looking at this?
Yeah.
So this acceleration, right, is going to be g. How about the time? How much time has passed between this event and this event? That much time. So is that the nicest way we can write that? Just leave it. Just leave it. No, you can write it much more nicely than that. Divide by 0? Oh yeah, get rid of the 0 first of all. He's extra. Sorry, Colin. I thought you were given a meme answer to that. What is g divided by the square root of g? The square root of g. Very good. If I'm going to show my work here, it's going to look like this. You know, I've got g. So let's break this up. Does everyone agree that I can do this? I can turn this into this. That's how square roots work, right? Just for example, the square root of 5/3 is the same as the square root of 5 over the square root of 3. This one, so hopefully you're familiar with that idea. Same thing here. And then I've got g over the square root of g. You know, I can think of this g as being root g times root g. If I wanted, cancel one of them out. Is everyone okay with turning this into this?
Sure. Yes.
You sure?
It's up to you, Mr. Hall.
What?
I said it's up to you. Whatever you.
It's not up to me. It's up to the universe. Now what can I do with these two square roots? Combine them again, and look at this. That's a pretty formula. That's a nice, elegant form there. Make sure you're, keep in mind, guys, if you do a problem together in class, make sure you're showing up the work and all that stuff. If you just write the final answer, I can't give you full credit for that. Okay. So 42, 43, 44, those three questions are a lot like this, where you're given some kind of scenario. They're all very, 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 very closely related scenarios you're going to find. So dropping a rock off a building has a lot of similarities to shooting a cannonball straight up in the air, or I guess those are the two symmetries right there. It's going up versus going down. So in those questions, I ask you to analyze them just with like letters. Every question there, I think we've done them with numbers, so you can always go back and look and see, oh, I've done this problem before with numbers. How did I do it? How did I break it down? How did I relate the quantities? And so, yeah, so tomorrow I'll have some time in class to kind of try to work through those. I can talk to you individually if you're getting stuck, but we're almost done. The only thing left for us to cover is really the graphic calculator problems, which and this time in their equation. We'll cover that really briefly. That's kind of an afterthought, but the graphic calculator problems, or also known as like Desmos problems, you can probably imagine, looking at this equation. We haven't done one yet where it starts off at some height, some non-zero height, with a non-zero velocity and its acceleration, and then like say it hits the ground or it reaches some other height. So we haven't done one yet where these are all non-zero numbers, and that's what, if you think back to like algebra class, right? If you have a quadratic equation with all non-zero numbers, you can solve that with either a quadratic formula, or for our purposes, we'll just use a graphing utility to get the answers. Use Desmos or something. So those are pretty easy. Those will be straightforward. So that's it for today.